Welcome friends. So we are discussing network theory, module 4, network solving techniques. In the last session we have discussed superposition theorem and we have also solved one problem on superposition theorem. Now in this part we will mainly discuss the most important theorem of all, Thevenin's theorem, most widely used theorems to solve network problems. And also we shall demonstrate the theory of the Thevenin's theorem with a numerical example. So let us go into the statement of the theorem. Again, purposefully, the statement of the theorem is split into 5 different parts. The first point states that for which type of network this theorem is applicable. Now, it is a general statement for all theorems that those theorems, superposition, now Thevenin's. Now, following to this, we will discuss 2 more theorems, that is maximum power transfer theorem and Norton's theorem. Generally, any network which is linear, active and bilateral, those networks, for those networks these theorems can be applicable. So it is a general statement for all the theorems that for any linear, active, bilateral network we can apply these theorems to solve any current or voltage. Now, suppose we have a network, any network, right? Suppose we have any network, then that network can be represented as a voltage source in series with the equivalent resistance with load resistance. So we can represent the network. What is the statement? It's that we can represent the network. We have a voltage source, we have a resistance and we have a load resistance. So any complex network we can equivalently represent any complex network by this simple network, which is a voltage source, we have a resistance in series and we have a load resistance. So this is RL, which is called load resistance. Now this equivalent resistance is called RTH and equivalent voltage is called ETH. And this current is nothing but ETH by RTH plus RL. Now what is that voltage source? This voltage source is nothing but, it's called Thevenin equivalent voltage ETH. So this is ETH actually. ETH stands for Thevenin equivalent voltage. Now what is that voltage? What is the definition of Thevenin equivalent voltage? It is the open circuit voltage across the load. So when you have the load, you should open it. So whatever voltage appearing across the load is called open circuit voltage. For an example, suppose we have a network like this. Let us say this is V1. Let us say we have R1, we have R2, we have R, we have a current source I1. So this is the voltage source. Now we want to measure the current flowing through this resistance R. So the first step is to remove your R to make it open circuit. So let me draw that. So this is voltage source V1, then we have R1, then we have R2, then we have a current source I1. So statement is that we first may need to make our load is open circuited. So load is open circuited. So whatever voltage appearing across this open circuit terminal is called E Thevenin voltage or Thevenin equivalent voltage. So it is the open circuit voltage across the load. So you need to load must be open circuited. So you first need to remove the load. So remove the load means you need to open circuit it. So whatever voltage appearing across that open circuit terminal is called Thevenin equivalent voltage. Now let us coming to the Thevenin equivalent resistance. Now the equivalent resistance is called Thevenin equivalent resistance RTH. So RTH is nothing but Thevenin equivalent resistance, right? So how can you measure? So what is the Thevenin equivalent resistance? It is the equivalent resistance of the network looking back into the open circuited load terminal. Now provided another additional condition, removing all energy sources, all energy sources. So with this, so now when you calculate RThevenin, what is RThevenin? You need to calculate the equivalent resistance of the network from the load terminal. So from here you need to calculate, from the here you need to calculate, it is RTH. Now provided one condition is there, you need to remove all the energy sources. Now how you can remove energy sources, that is already discussed in case of superposition theorem. If it is a voltage source, it should be shorted. If it is a current source, it should be open. So looking back into the terminal, you see this phrase, looking back into the open circuited load terminal, that means you need to measure from the load terminal. You need to measure it from load terminal. So with respect to this load terminal, RThevenin is nothing but R1 for this circuit, for this network, right? So this is Thevenin equivalent resistance. And last, once you have got Thevenin equivalent voltage and Thevenin equivalent resistance, you must construct Thevenin equivalent network. What is that Thevenin equivalent network? This is Thevenin equivalent network. That is a Thevenin voltage source equivalent network. What is Thevenin equivalent voltage network? We have a Thevenin voltage source in series with Thevenin resistance and in series with load resistance. So this is called Thevenin equivalent network. Thevenin equivalent network. So from that Thevenin equivalent network, we can find out the current flowing through the load resistance or current flowing through the resistance through which we want to measure the current. So basically it is I. Just it is written here, I is equal to E Thevenin by R Thevenin plus RL. So it is very useful and mostly used theorems amongst all. So current flowing through them is E Thevenin divided by R Thevenin plus RL. So let me So gist, let me make a gist that Thevenin Thevenin's theorem, suppose you have a network, suppose you have this network, let me give you another example. So this is any network, rough network, any arbitrary network. Let us say V1, let us say this is V2, this is R1, this is R2, and this is R, or RL rather, which is our load resistance. So what will be the current flowing? So according to the Thevenin's theorem, what are the steps? You need to first open circuit RL and measure or rather calculate VOC, or that voltage is called Thevenin voltage. So when you remove or when you open circuit the load resistance, how this network will be looking like? So this is V1, this is R1, this is R2, this is again V2, another voltage source. So now you are making, this is open circuit, so this is ETH or open circuit voltage. So whatever voltage appearing across these two open circuit terminal, it's called E Thevenin or open circuit voltage. So the next, what is the next step? To calculate, measure or calculate RTH. How? It is the equivalent resistance of the network, equivalent resistance of the network measured from load terminal. That is very important, measured from load terminal. So that is very important. So for this circuit, now in order to do that, you must remove all energy sources, all energy sources must be removed. So with this, what is this? What is the equivalent circuit to measure the Thevenin resistance? So we have R1, we have R2. So we need to measure R Thevenin from this load terminal, right? So you need to make V1 shorted, you need to make this V1 shorted, you need to make this V2 shorted, make it deactivated. So from this load terminal you want to calculate R Thevenin. So for this circuit, with respect to these two terminal, there are two different paths, one along this R1, another along is R2. So for this network, R Thevenin is nothing but R1 parallel R2, right? And the third step, construct Thevenin equivalent network. What is that? Thevenin equivalent network is, that is the open circuit voltage, which is Thevenin voltage, in series with RTH, and then we have RL. So this current is equal to, now from this a simple circuit we can evaluate this I as ETH by RTH plus RL. So these are the three different steps through which Thevenin's theorem, problems on Thevenin's theorem can be solved. First, you measure ETH. Second, you should measure RTH or calculate RTH. Then you must calculate or you construct Thevenin equivalent network to calculate current using this formula. So with this background, we try to solve one problem. So let us consider figure 15. Let us consider figure 15 where you need to evaluate power loss in 10 ohm resistance. Power loss in 10 ohm resistance. So this is the 10 ohm resistance. So you need to calculate power loss is 10 in 10 ohm resistance using Thevenin's theorem. Now power loss, as you know, power loss is nothing but I square R. Power loss is nothing but I square R. So in order to calculate power loss or voltage drop across resistance, you must calculate current flowing through that resistance. So this problem is nothing but to calculate current flowing through resistance. Let us say that current is I. So the current flowing through the 10 ohm resistance we will measure shortly, or we will calculate shortly using the Thevenin theorem. Once you calculate I, then power loss will be calculated by I square R. So step by step we shall see. So let us make first our Thevenin, that is this is the load, that is the what is load? That means the resistance through which we want to calculate current, that is load resistance for us. So for some another problem, if we want to measure the current through this 5 ohm resistance, so for that problem 5 ohm resistance is the load for us. So the load resistance depends through which we want to measure the current, right? So the first step, you need to remove the load resistance. So let me draw the diagram circuit. The step 1, we have this 1 ampere current source. Then we have this 2 ohm resistance parallel. Then you have 5 ohm resistance. Then you must open circuiting it. And then you must have this 10 volt source present. So this is the equivalent circuit. That is the step 1. So this voltage is nothing but ETH. So now luckily for this problem, the E Thevenin can be directly obtained using this circuit up to this shaded by yellow. Luckily for this problem, because you see the voltage source, even if the load is removed, it is open circuited, the voltage source is appearing directly across this open circuited terminal. Voltage source is directly appearing across the open circuit terminal. That is why we can directly, luckily for this problem, we can directly write E Thevenin is equal to 10 volt. We can directly write E Thevenin is equal to 10 volt. So in one way, the Thevenin voltage is independent of this part shaded by blue. It does not depend, okay? Does not depend on this part, remaining part of this network shaded by blue. So as we open the load, that source voltage, that is 10 volt, will be directly falling across this open circuited terminal, so we can directly write that Thevenin voltage is 10 volt. That is step number 1 for you. Now second step, so see, this is the solution. Now the second step, you must calculate RTH. Now what is RTH? RTH you must calculate from the load terminal, keeping all sources are deactivated. So how you can deactivate 10 volt source? It should be, it should be deactivated by making it short circuit, and by making open circuit you can deactivate a current source. So we can write the equivalent circuit. You can draw the equivalent circuit of Thevenin equivalent resistance. Let me draw first 3 resistances, 5 ohm, then 2 ohm, then this is the load terminal, then we have a voltage source, then we have a current source. So this is 5 ohm, this is 2 ohm, and from here we will measure RTH. Now this should be short circuited because this was a voltage source, so it should be short circuited, and it is open circuited current source. Now with respect to RTH, now if you see this network, with respect to this RTH terminal, there are 2 paths, no doubt. One is this short circuit path. So this path is short circuit effectively, right? This path is effectively short circuit path, and another path is this path with resistance of 7 ohm. Because these 5 and 2 ohm are connected now in series effectively, because this is open circuit terminal. So with respect to this load terminal, there are 2 paths. One is 7 ohm and another one is the short circuit path. So effectively, as you can understand from this circuit, that this 7 ohm resistance is directly short circuited. So from this network we can directly write RTH is equal to 0. Why? Because you just imagine one current will be injecting from this terminal like this. One current is injecting, one current I is there from is being injected from this open circuit terminal. Just imagine, now it will getting 2 paths, one along the 7 ohm resistance and another one is this short circuit path. So from the knowledge of current division rule, so current will always try to flow through the minimum resistance path. So this entire amount of this current I will be flowing through the short circuit path. No current will flow through the 7 ohm resistance. So effectively the 7 ohm resistance path is out. So effectively, even if it is present in the circuit, but effectively this is out, it is ineffective. So the entire current, if it is flow imaginary, please imagine if a current is flowing, so that entire current will be flowing through the short circuit path. So Thevenin equivalent resistance effectively, if we measure or if we calculate, it will be effectively this value, it will be 0, right? Because this is the, with respect to this open circuit terminal, with respect to this open circuit terminal, this is entirely short circuited. That is why we have RTH is equal to 0. So finally, third step is the Thevenin equivalent network. Thevenin's equivalent network. So we have a ETH which we have evaluated as 10 volt, right? Then in series with RTH which is equal to 0 ohm, that is why it is represented by a short circuit. And then we have a RL which we have observed or which we have assumed as 10 ohm, right? So this is 10 ohm. So when you calculate the current, it is ETH by RTH plus RL. So in the numerator we have 10 volt, in the denominator it is 0 plus 10. So current will be 1 ampere. So once you have calculated current, so it is I square R is the power. So 1 square into 10, so it will be 10 watt. So using the Thevenin's theorem, we have evaluated power loss in 10 ohm resistance, which is answer is 10 watt. But irrespective of the power loss or voltage drop, one thing must be done. You must calculate the current flowing through the load resistance. Once you have done the current part, you can evaluate I into R, that is voltage drop across that resistance, and power loss, that is I square R loss. So this is the Thevenin's theorem for you. We have solved one problem. In the later stage of this course, we shall show you, or we shall solve you more variety types of problems on this theorem. So this is the initial stage, so we stick to this simple problem for the time being. So we have discussed Thevenin's theorem. There are three fundamental steps in this theorem. First, load resistance would be open circuited, and you need to check what is the voltage appearing across that open circuit voltage, and that open circuit voltage is called Thevenin voltage. That is step number 1 for you. What is step number 2? You need to calculate or measure Thevenin equivalent resistance. What is Thevenin equivalent resistance? It is the equivalent resistance of the network measured from or calculated from the load terminal, open circuited load terminal, provided all energy sources must be removed from the circuit. Voltage source must be short circuited, and current source must be open circuited. So once you have done these two, one is Thevenin voltage and number 2 is Thevenin resistance. Now you must construct the Thevenin equivalent network. What is that? Thevenin equivalent network is the Thevenin voltage is connected in series with Thevenin resistance with the load resistance. So once you do that, you can easily find out the current flowing through the load resistance by a simple formula, ETH by RTH plus RL. So with this, a very complex network can be solved very easily, very effectively by this theorem. Once we can able to bring down a complex problem or complex network into simple problem, simple network containing a voltage source in series with a resistance with a load resistance. Simple. So with this, I am concluding Thevenin's theorem. In the next part of this module, we shall start in the next phase, that is maximum power transfer theorem. So with this, I am ending. Thank you.